Good morning. My name is David O'Sullivan. I'm presenting this for NASGTBC. It's a BC chapter of the North American Society of Trenchless Technology, which of course is a part of the Trenchless Society of the worldwide organization, which is an organization there to promote and set standards for trenchless technologies. So I just want to I'm talking from British Columbia, from Vancouver, British Columbia. So I want to talk about the importance of utilities first of all. And we need to recognize the importance of utilities. In the early 2000s, there was a question asked to the readers of the Lancet, the eminent British medical magazine, what was the most important advancement in medical advancement in the last 175 years? The answer that came back was underground piping. Water and sewer, not anesthetics, not surgery, not antibiotics, but water and sewer. And it does essentially account for I'm proposing about 35 years of our lives. If we didn't have clean water and sewers, we'd be dead by about 45 years old, as is evident in the third world. And it takes us up to about mid-70s, where we then start to depend on our healthcare systems in the first world. So it's the difference between the third world and the first world is water and sewer. In the lower mainland, British Columbia alone, just to give you an idea, and this is just typical of most cities, according to the Waste Management Act reports that go in every second year to the province of British Columbia, there's about $20 to $30 billion worth of infrastructure that's just stormwater and sanitary in just the lower mainland. That's in a city of 2.2, 2.4 million people. So $20 billion. If we assume a replacement rate of 1% or once every 100 years, which is quite aggressive, that's about $200 million a year in replacement work that needs to be done. And of course, it's not being done. On top of that, we have a further 25,000 culverts in the lower mainland under roads and highways. These are corrugated steel culverts. And then I'm going to talk today mainly about using trenchless to replace these rather than traditional open cut. The reason I'm talking about trenchless is it's something I've come to the conclusion about in the last number of years. Not alone is it economically viable and feasible to use trenchless technologies, but I think we owe a duty to society to look at doing as least damage as possible and yet maintain the utilities that I talked about at the start of this slide to maintain the society that we now enjoy. One of the big benefits of using trenchless technologies is that our carbon emissions are reduced drastically. We do not have to excavate down to the pipe or pipe zone, remove all that material, haul it away, dump it, bring new material back in, all to install a pipe that's 200-300 millimeters in diameter. Because invariably the trench that we have to install now, because of safety concerns and so on, is probably about 1.5 meters wide and about assuming we're 2.5 meters deep. Also included in that trench, of course, is the disruption to the surface, the asphalt. We degrade our asphalt by putting cuts in it, causing the lifespan of that asphalt road to decrease by about 15, 18, 20%, depending on the traffic loads. We cause diesel particulate to go into the air, which causes problems with healthcare, which of course is another calculation. It comes in under the healthcare issue. And we cause disruption to traffic. You've all been stuck in the traffic, sitting there. Well, if you look at the cars behind you, and let's assume there was 1,000 cars sitting there. 1,000 cars it's not out of line to assume that each of these vehicles is worth $40 an hour. Or if you've got a 20-minute delay, that's 1,000 cars is $40,000 per hour, or $1,700 for 20-minute delay. That's $17,000. $17,000 is a big cost to society. At both morning and evening rush hour, that's $34,000. You add that up across the city, suddenly you start talking about millions of dollars a day in disruption by using open cut construction versus trenchless. So today we're going to talk about both the rehabilitation and new construction methodologies that are available through the use of trenchless technologies. I'm going to look at, first of all, rehabilitation, because that's mostly what we think about when we look at trenchless technologies. When we talk about pipe rehabilitation, what we've got to go back and step back a second. We've got to look at the definition of what is a pipe. What is it there for? What does it do? Well, first of all, it's a vessel to contain a liquid or a gas, but to contain a liquid. And so the functionality of that pipe to contain the liquid depends on the liquid that's in it. If it's a storm sewer, it doesn't have to function that well. Obviously, if it's petroleum or it's a natural gas, it has to perform 100% and totally contain the liquid. If it's water, surprisingly, we have allowable waste or allowable leakages in water pipes. But sad to say that a lot of leaks from the water pipes are becoming more and more, and some cities are losing 30, 40, 50% of their water, their treated water, out through leaking water pipes. The next issue is its ability to transport that liquid. Is it big enough, in other words? As we densify our neighborhoods, the pipes that we put in 50, 70, 100 years ago are now too small. Therefore, we have to upsize those pipes to make them big enough to transport the liquids that are now being demanded of them due to the densification of areas. And the last one is the structure of the pipe. It has to maintain a tunnel. If that pipe starts to fail, and this is more relevant in culverts than it is in smaller pipes, but smaller pipes do collapse as well. So is the structure good? And the reason I'm breaking it down this way is that the rehabilitation that we're talking about in Trenchless is able to handle or is able to deal with any one of these issues and therefore bring life back into that pipe and give us back 70 or 100 years of lifespan again. So we're going to deal with CIP. We're going to deal with these following topics. I'm not going to read them out to you because we're going to deal with them in more detail in a few seconds. CIPP. CIPP was one of the first methods of rehabilitation. It came out of work done in the UK back in '71 by a man called Eric Wood, who started a company called In Situ Form. There are other ways of rehabilitation, by the way, which we'll get into as well, but the CIPP is one of the most prominent ones. It is a closed fit liner. It is essentially a fiberglass or felt sock which has resin impregnated into it. The pipe that is pulled into the existing pipe, it is blown up either by steam or air, pushed tight against the host pipe, and then caused to cure. And whether it's caused to cure by hot, but it's caused to cure, and then you end up with a fiberglass pipe inside the existing pipe. It therefore will seal. It'll handle the issues of the first one, which we talked about now, was the vessel going to contain the liquid. Now we can put a new pipe inside will contain the liquid. And or if we've got extensive cracking in the pipe and we feel the structure is about to go, we can put this in and that will stabilize the pipe. It will not handle an increase in flow, not completely. The fact that its end value, its internal end value is quite low will cause somewhat of an increase in capacity, but not in the way that we can increase the capacity in other ways. It can be used in sewers and or pressure pipes, and it is, as I said, it's a closed fit product. Here is what we're doing. We're doing a wetting out process. So we've got a roll of felt that is pre-manufactured. It is the diameter that is required for the particular job. So it might be 200 millimeters, 600 millimeters. In this case here, I would guess it's about 900 millimeters. We induce a vacuum into that felt with a vacuum pump to create a vacuum. So that felt liner is in a tube, and then it's got a coating on there or a wrap on there of plastic, like saran wrap type of plastic on the outside of it, and so it's sealed. So then by introducing a vacuum on the inside, we've sucked all the air out of the inside, and then just downstream of that, we introduce resin. And so the resin goes into that vacuum and essentially saturates the foam. Or you can use fiberglass, or you can use Kevlar. There's lots of different processes that are products that you can use to give the structural strength on these products. So the resin is introduced. Again, the resin is designed depending on what the product is. If it's sewage, is it a gas, is it a chemical that you're trying to transport through this pipe? You can change the resins accordingly. The resin is introduced. Then it is soaked into all of the fiberglass or felt, and then the whole process is pulled through that machine in front of you, which is a roller. That roller, because you know the strength of the resin that you're introducing, you know the thickness of the felt. What you're doing with that roller is you're setting the final thickness of the pipe. So if the design comes back and says you need a 25 millimeter pipe, you would set those rollers at say 53, 55 millimeters apart, which gives you your double 25 by 2 plus 2 or 3 millimeters for safety. Then that material has got the resin and the catalyst in it, so it will set up once it gets to a certain temperature. So that product is taken and put into a refrigerated truck. That truck keeps it down as close to zero as it can and keeps the resin from kicking off. It will last in that truck a week, 2 weeks, that kind of order of magnitude. It is then taken to the site in this manner, in a refrigerated truck, to be introduced into the host pipe. You see in the top photograph here, so what they're doing there is they're inverting that pipe. So as I said to you earlier, there was a plastic on the outside. Now you're inverting it like you put your sock on, and that the plastic becomes on the inside. On the right-hand side, you can see that one of the big benefits of CIPP is that it can be introduced through a manhole with no excavation at all. Absolutely no excavation. You put it inside the pipe, you pressurize it to make it fit the host pipe, and then you cause the resins to kick and to go off and become hard. Then you cut off the ends, and then you can go in with robotic cutters and cut out your laterals. The photograph in the middle, lower with the red background, it says installation. That is the actual inversion process inside the host pipe. So the host pipe is red in that case, and this is inverting and moving along. You can see a little extra pool of resin on the bottom. So that resin will bond into the host pipe and cause a bond between the host pipe and the new CIPP pipe. And then as the inversion is finished, on the right-hand side where it says finished CIPP, that's a finished product. And now you see, if you notice at 7 o'clock or so, you see that band of writing. Well, that band of writing was also at the very start when we were putting resin into it. That's the plastic wrap that's around the fiberglass. And so now that plastic wrap has come on the inside, not rather than the outside. Here is your typical finished product, just doing a cross-section through it. So the pipe on the outside of white is the existing PVC pipe, and then you've got your CIPP pipe on the inside. And again, you see that joint of the plastic on the right-hand side here at about 5 o'clock, that little white line going through there. That's the plastic on the inside again. So here's your typical resin or CIPP pipe and a CIPP pipe totally rehabilitated. Here's another product. This is a spray-on. So the CIPP pipe we talked about a few minutes ago can be designed either as a standalone, or it can be designed as a composite product. In other words, if you're looking at a pipe, let's say 600 millimeters or 900 millimeters, you don't really want to put a CIPP pipe in there that is so thick that it displaces the existing pipe completely. There's no need for that, unless the existing pipe is totally gone. What you would do is put in a composite product so that your CIPP will augment the strength of the existing pipe, or if it was just a case that the existing pipe was leaking, and you put a CIPP pipe in, you put in the CIPP pipe in to stop the leaks, but you're depending on the existing pipe for the structure. In this case here, there is really no structure from this product here. It is a polyurea that you're putting in here. It is a coating that is going on. It does have the ability to span holes and to span leaks in the pipe. And what it's doing is it's providing the ability for the pipe to now hold water again. It also helps us in the case of water pressure pipes. Of course, it's a C factor, not an N factor, which is the friction factor of water going through the pipe. So it does help to restore your friction factor because, of course, in water pipes, we often get a lot of materials building up on the inside and a corrosion, and this stops that happening. You can do this in one day. It depends on the consulting engineer, depends on the engineer of record who manages this pipeline, who has the license to have this water pipeline, if they're willing to do that or not. A lot of places do it and put it back in one day and then do a boil water advisory for 3 or 4 days after that. Risoline 320 is one product that conforms with the STM standards here, and it's good for 50 years. So you're adding another additional 50 years to the life of your pipe by doing this. Here's an example of what your water pipes can be. So the water pipe on the left is an existing water pipe. That's the corrosion that I talked about on the inside. So you can imagine that the C factor, or the ability for that pipe to carry water, is quite reduced because of the corrosion between the water and the cast iron or ductile iron pipe. And on the right hand side, you've cleaned the pipe, and then you've put the polyurea on the inside of it. So that's the pipe on the right hand side. So you can see that the increase in capacity and the longevity, and you've sealed any holes that are in the pipe. Out of water pipes down into a corrugated steel structure, culvert. So we're talking now about a much bigger pipe. This was a pipe in the city of Richmond, just on under Highway 99, which becomes the I-5 in the US. This pipe had failed on the right-hand side, and this is what's called an exit control culvert, which means that there is standing water in the pipe all the time. Therefore, the invert of the pipe in this case is probably in pristine condition. The overt of the pipe, as you can see in the top of the photograph here, is in great shape. So it is just at that band area on the sides that, typically 8 and 4 or 9 and 3, that has failed. And in this case, within 150 millimeters, 200 millimeters above and below that failure band there, the pipe was a full 6 millimeters in thickness. But at that band, it had failed the whole way along. I'm not sure exactly why. It's probably to do with water and oxygen levels. Here is an exit control culvert. So an exit control culvert is one where the water goes through and doesn't remain in the pipe, standing in the pipe. It just flows right through, and you tend to get bed loads and rocks. The exit control culverts tend to be sloped and steep, whereas the entrance control culverts, the exit control culverts tend to be flat. The entrance control culverts tend to be steep. The entrance control culverts tend to have bed loads and rocks and gravels coming through them, which corrode the invert through abrasion. Here you can see the abrasion happening, and then it goes through. And then what happens is that the materials, the bedding on the outside tends to get inside, and bedding around the corrugated steel pipe it's like the concrete on a normal beam. It's the compression part of the structure, whereas the corrugated steel is the tensile part of the structure. Whereas concrete is the compression part of a beam, whereas the rebar is the tensile part of the beam. Well, here, if you lose your gravels on the outside of the pipe, then you've lost your compression part, and if you lose that, you lose the structure. So you get a failure of the pipe. Here is a product that is great for rehabilitating these pipes. It's a sprayed-on centrifugally applied product. Now, whether you're putting on a geopolymer, whether you're putting on a cementatious product, whether you're putting on, it doesn't matter what the product you're putting it on. That's a design issue. It's the application is the situation here, and this is put on with a spinning head, either electrically or air-powered spinning head. Here's a more conventional. This is when the pipe has failed, generally down at the 8 and 4 or even 9 and 3. So what we're doing is we're bonding an existing pipe, so we're making a composite product. So the bottom becomes a concrete pipe, continuous concrete pipe without joints, and is bonded to the steel. So then the steel on the overt, or on the roof, if you want, of the pipe, being in perfect condition, is reutilized to continue on to provide service for a further 70 or 80 years. This is a key part of rehabilitation. So we're using the existing structure, the parts of the existing structure that are still in good shape. And what we're doing is augmenting that existing structure with the part that has failed and building a new section to the part that has failed. In this case, we're concreting the floor of it, and we're shotcreting the walls of it. All of those previous products that I talked about were what we call closed fit liners. They were very close to the edge. They maybe augmented the flows a little bit because of the N value or the C value, but they didn't make it bigger. They made it the same size or as close to the same size as possible. Now we talk about slip lining or loose fit liners, or rehabilitation, internal rehabilitation. It can be used again in pressure pipes or in sewer pipes. You do lose diameter. That's one of the issues here. What you're now doing is putting a pipe inside a pipe. And so the pipe inside the pipe, and then you've got an annulus between the new pipe and the old pipe. That annulus generally has to be grouted. Doesn't always. In water mains, you don't have to grout. The Europeans don't tend to grout. North Americans do. So there's different opinions as to whether to grout or not. Pipes can be introduced by various methods. It can be pull-in hole or folded down or collapsed in some way. The other issue, the big issue here, of course, is this pipe that we're putting in now. The slip line pipe is made by others. So it takes part of the responsibility from the engineer of record away, because all of the other processes that we talked about there were the process, whether it be the concrete, the CIPP, the resins, they were all made, or the process happened in the pipe on site, which meant that you were both rehabilitating the work and creating the product on site. From now on, we're going to talk about slip lining, whereas the product that you're doing the work with is made by others. It's made to a controlled inside the factory, not on site. Here we're looking at a folding form. So what we're doing is we're taking a plastic pipe here. It's not your typical plastic. It's a slightly different formulation, but it's deformed elastically. You don't take it to its plastic limits, obviously, even at those extreme bends of that U that's in the middle there. That still is not a plastic deformation. It's still elastic, and when you pop this back up, it will form a brand new pipe. It is folded, and of course, by doing this, you can actually get the annulus to be a lot smaller than you would do if that was just a circular pipe that you were trying to pull in. So it allows you to pull in a much bigger pipe, much closer to what you would get with a CIPP or a no annulus type of product. But what you are doing, of course, is you're putting a whole new pipe inside. So what you're doing, if you remember way back to my carbon slide, what I talked about was that pipe that's way down the ground, 2.5 meters down. What we're doing is we're just rehabilitating that pipe inside. And so all of the other material that I had to excavate, which is at 2.5 meters deep by 1.5 meters wide, what we're doing with all of these rehabilitation methodologies, we're eliminating that action. We're eliminating hauling all that material away. All we're doing is working within the existing pipe with all these methodologies. And so here we've got on the right-hand side, again, we've got the fold down. In the top right, you're folding it down, and that's high-density polyethylene pipe. And then you see it coming out of that machine folded down. They put straps on it or just tape on it about every 400 millimeters. And then you introduce it to the host pipe. You seal off both ends of it. You put air onto it, air pressure onto it, 5 or 10 pounds, and it causes all those bands to pop. The pipe pops up and back into its circular shape, and you've now got a new pipe in. Or you look at the left-hand side there, and you're slip lining. So when you slip line, you have to have a bigger annulus, and you're just slip lining this pipe through. In that case, you can see the annulus there. It's at maybe 50, 60 millimeters. So you're losing that capacity. There is another process that you can do where you can swage line. So you can actually pull high-density polyethylene, because again, high-density polyethylene has a great ability to elastically deform before it yields. So you can elastically deform the pipe, stretch it out, in other words. And so you're taking the diameter down by 10, 15, 20%, pull it into the host pipe, and then let it spring back, if you like. Now, it doesn't spring back as such. It goes back to its old shape over a period of hours and forms a closed-fit liner that way. Here's another product. This is a product that's premise line. It's a product out of Germany. This came from the oil and gas industry. Because, of course, the oil and gas industry is famous for having to put water down into oil wells to push the oil back up again. And a lot of these pipes that would have been put in would have been steel pipes. They would have been used for 10, 15 years. They're in the North Sea. They're in the Gulf of Mexico. It wasn't a big concern, the fact that there were steel pipes and the coatings on them. Then they found they were using the pipes longer and longer, and they were starting to get failures in the pipes and corrosion. So they were looking for ways of rehabilitating it. This was one of the ways. The other one was swage lining, our high-density polyethylene liners in there. Again, the steel pipe was failing from the point of view of corrosion, pitting, and getting pinholes in there. But structurally it was fine, but it couldn't contain the liquid anymore. So what you had to do was augment its ability to contain a liquid, and here was one of the solutions, a premise pipe. The blue on the outside is a sacrificial layer, essentially, so that when you're pulling it through the steel, that blue will scratch and be scratched and save the other coatings in there. The beige material is actually Kevlar, so that gives it its strength and its hoop strength, and the black inside then is the is the product that contains the liquid. So if you go back again to our first premise that the first issue was the vessel to contain the liquid. Well, the black handles the containment of the liquid. The beige is the third area, which contains the liquid and is the pressure of it. And well, the size is the capacity, is the diameter is the capacity, which is the issue 2. Because of the Kevlar, you can handle enormous pressures, 1500, 2000 psi in this kind of product. You do end up having to derate it every time you go through a bend, but this can go around bends. This is a great product. It can be put in, up to 1,000 meters at one shot for a force main or a supply line. It can go in and be done in a matter of hours. Particular ends on a flange end, but it can go around bends. It's great for a pressure main or something like that. Back to slip lining again. Here is a slip line for a brick sewer line. When you go back and you look at our carbon photograph, which was the carbon slide which we talked about with the trench, normally that's how we put pipes in right now. You've got to think back in 1850s, all the way up to about the 1910s. We didn't have excavation machines. We were digging trenches by hand. Therefore, if I had to do a trench that's 5 or 6 meters deep, that's an enormous trench to try and dig by hand. So what we tended to use at the time is we tunneled. Big issues in London at the time when they put the sewer system in the 1850s, 1860s, 1870s, they tunneled the sewer lines in. They did not open cut them down 5, 6 meters deep. They tunneled it. This was a case in Victoria, the city Victoria, in the southern end of Vancouver Island. That was a tunneled sewer line under a graveyard that was put in. Very, very common in eastern US, eastern Canada, all through Europe. These tunneled pipes, and they're hand-built pipes. So the cross-sectional area was not consistent. It was probably consistent within the job, but it wouldn't be consistent for all jobs at the time. So the pipe was starting to fail after 150 years, and we ended up putting in a fiberglass pipe. This is a GRP, or a fiberglass pipe, that was made in Dubai and is introduced through slip lining. Here is a corrugated steel pipe that was failing underneath some hot baths in eastern British Columbia. Again, the same thing. This pipe here is about 3.3 wide, 2 meters high, so you could probably drive a pickup truck through it. It had started to fail because it was corrugated steel. This had a very high bed load coming down from the Rocky Mountains, and the invert of the corrugated steel pipe was just being abraded away. So the pipe was starting to fail, and we talked about that. It's an entrance control culvert, so the invert was being abraded away. We were starting to lose the material outside, so we're starting to lose the structure, and this is one of the ways of rehabilitating it. Here is another pipe. So the previous one I just talked about was the invert was abrading away. This one is a wood stave pipe. Wood stave pipe in North Vancouver. It is starting to fail through load because wood stave famously can yield. And the problem with wood stave is that the pieces of wood are put together with a slight little groove in them, but they're really like a barrel, and they're all in compression. Once you get to a certain point, as you can see on the left-hand side, it's starting to go oval. Those boards can pop, and once they pop, the whole thing just fails catastrophically. So what we ended up doing is slip lining, again, a GRP product in there, and stabilizing that ovality by grouting it, so creating the structure that way. By the way, there was a number of utilities on that road that's going perpendicular to this photograph. Large utilities, Metrovan, had major water mains, sewer lines, electrical lines. So the ability to dig that up was very, very slim. Here is a case of a live flow slip line. In the early 70s, late 60s, early 70s in British Columbia, in any case, a lot of sewers were installed to pick up what would have been local sewer systems that would have drained areas or dealt with areas and drained it out into rivers or oceans, and would have just gone into the ocean. The major governments at the time deemed that they pick up all of these sewer lines, capture them, take them down, and take them into major treatment plants. So a lot of these pipes were put in the 50s, 60s, 70s. They're now coming to the end of their lives, or there's other issues happening with it too. A lot of hydrogen sulfide. Because they were big pipes, I'm saying when I say big, 1.5 meter, 2 meter pipes, 3 meter box culverts, they were concrete, of course. And we now know that concrete has issues with hydrogen sulfide. And the hydrogen sulfide tends to eat the concrete, and we tend to get failure of the pipe and corrosion, especially if you get the hydrogen sulfide gas, which we tend to get when there's a bit of a gap between the top of the sewage and the overt of the pipe. So we get failures in these pipes. When you go in to rehabilitate an existing sewer line, of course, we can't get 300,000 people to stop using the bathroom for 3 or 4 days. So we have to either bypass or we have to work in the live flows. To bypass a sewer system, is a very, very expensive and very high risk problem. One of the issues we've got, of course, is that these so-called sanitary sewers are not totally sanitary sewers. There's a lot of when we talked about our basic issue with the pipe and the fact we have leaks, in a sewer system, we don't have leaks out like you have in a water main. You have leaks in of groundwater coming into the pipe. And that's tolerated to a certain point. But what happens is that in heavy rain situations, we can get increases in flow of 4 and 5 times the base flow in a storm situation. This causes major issues to happen. And so when you're bypassing, you have to have sufficient capacity to handle those major increases in flow that happen, during major storm events. So it makes bypassing a very, very expensive system to install, and it can often be 60-70% of the actual cost of rehabilitation, because rehabilitation is incidental in comparison to the bypassing. A system that has been developed in the southern US is live flow slip lining. So you're actually going into the pipe while the flow is still happening, and you're inserting the pipes in live flow. Now you're obviously doing it in the summer situation when there's not winter flows in there, but there is still the flow that's happening every day. And of course you can see the variations in flow when we all get up in the morning, we use the bathroom, so we get that 8 o'clock flow starting to happen. By the time it got to this particular area, it was about 11 o'clock. So we can see the flow starting to come up from about 8 or 9 o'clock, peaking about 11, then dropping down by about 1 o'clock, and then low flows continuing on through the afternoon, then coming back up again in the evening from 6 o'clock on until about 8 or 9 o'clock, when we then stop using and go to bed. And then at night, the flows drop right down and maybe only 400 millimeters deep in the pipe at that point. That one there you can see is above the spring line of the pipe. That was probably about 12 to 1 o'clock in the afternoon. Here is a case of slip lining a corrugated steel pipe in Delta. This is a corrugated steel pipe that's failed. Rather than putting in a pipe or rehabilitation of the sprayed on concrete that we put in earlier, we're putting in a corrugated steel pipe, a whole corrugated steel pipe, and grouting the annulus in there. Okay, we're going to move on to the second half. The second half is new construction. New construction is rather than a rehabilitation we just dealt with, we're going to deal with the new construction. We're going to deal with the following topics. I'll get them into them in detail in a second. So, horizontal directional drilling is probably the method that we most know about when we talk about new construction. It's something we've seen everything from a 25 millimeter water service or your fiber optic cable being put into your house to a process where we're putting in a 600, 800 across the Fraser River, Mississippi, the Congo, Rhine River, whatever. And so it's a process that's used for installing a pipe that is generally not a gravity pipe. It can be used for gravity if you have very tight controls in your grades, but it's generally used for a pressure pipe type of situation. As I said, lengths up to 4, 5, 6 kilometers, depending on what you want to do. This is the process here. So you are drilling in with a drill rod, depending on the size of the rig that you're using. The drill rod might be anywhere from 25 millimeters in diameter up to 200 millimeters in diameter when they're using the drill type of rod that they use in oil well drilling. Horizontal directional drilling actually came from the oil fields. So when you see the rig that we normally see from an oil rig, it would have gone and then gone down into the zone where the drill pipe and gone off laterally, trying to pick up a reservoir of oil that could have been a half a mile or a mile or two away. that wouldn't have paid to locate a rig over that particular deposit of oil, but it did pay to try and drill and horizontally drill from the one base. This was particularly common in the North Sea, where you weren't dealing with just a rig on the ground in dry land, but you were dealing with a rig out in the oceans, and relocating a rig like that is. So they use this as a process to try and capture pockets of oil around where a rig was located. So then we've used it. It's come in, and we're using it in the municipal side and our utility side. I believe Charrington was one of the first people to get into this in California back in the 60s. It is a process, as I said, you're drilling down. As you go straight, you're rotating the rods at, let's say, 40, 50 RPM. Then when you want to stop and you want to change direction, as you can see there as the drilling down, it changes direction, you will stop the rod in 12 o'clock position, and you'll push straight. That will cause the rod to go up, or in the case of change from the incline, to go flat in that case. The front of the rod has either a flat plate on it if it's soft material, or if it's rock, it has a trichome bit on the front of it. And that plate and or trichome bit is bent from the direction of the rod by 5 or 6, 7 degrees. And inside in that first section, that first, say, meter and a half of height behind the trichome bit or the flat plate, is a sonde which is sending material or information back up to the operator of the rig. It will send them back rotation, so they'll know if it's 12 o'clock or 3 o'clock or 6 o'clock, inclination, to know how inclined the head is, depth, and then a number of other parameters such as temperatures of the drill rig and the head and such like that. That's how they control it. So they can either walk over, or they can put a wire grid on there. There's depending on the size and the process, but they can control where the rod is, what its inclination is, what its rotation is, and from that steer the rod to get into the perfect condition. And when you're doing the process, it is like it's akin to drilling a piece of steel. So you'll start off with your pilot hole, and then you'll verify the pilot hole is exactly where you want it to be, and then you will put on what they call a reamer, or if you're drilling a piece of steel, you use bigger and bigger and bigger bits. So you ream the hole out. You make the hole bigger and bigger until you make the hole, in the case of a pressure pipe or a non-gravity pipe, make the hole about 150% of the diameter of the product pipe that you're pulling in, and then you pull the product pipe in at the final pullback. What you're doing as well when you start drilling is you're using bentonite as a material to go down to drill through the center of the drill pipe. That bentonite mixes with the cuttings that you're creating with either the flat plate or the trichome bit. That bentonite mixes with those cuttings, and that bentonite comes back up. And if you look at the pipe on the right, or the reamer on the right, you see that white band on both sides. That's actually an air gap, or a gap. The bentonite comes back up through that with the cuttings up to the hole on the left, that beige hole on the left just in front of the rig. The bentonite, the cuttings and bentonite come up into that hole. They're pumped off, they're put through cleaners, they take out the cuttings, and they use the bentonite back in the rig again to pump down. The bentonite also tends to cool the reamer head on the front and keep things cool. It also tends to keep the hole open. Obviously, if you're with the trichome bit, you're in rock, you're not worried about keeping the hole open. But if you're in clays and sands and silts, you are worried about keeping the hole open. And what you're doing is you're balancing the weight of the bentonite with the tendency for the hole to collapse. So you make the bentonite as thick as you need to counteract the tendency for the clays or the sands to try and collapse, or sands and gravels even. As you start to get into gravels, it starts to get very, very difficult to counteract the ability of gravels to try and collapse because of the point load of a piece of gravel at one. It will just sink through the bentonite. So once we get into gravels, we end up having to put casing pipes in to get through the gravels, to get into the rocks to drill through. But these are, I don't want to get into too many details on it. I'm showing you this hole here because of this path here, because it's important that we understand the process of directional drilling. If I want, in this case, I'm just using this as a path for putting in a sewer line, or sorry, a pressure pipe, like a water pipe or an oil pipeline, under a creek. If, however, I was using directional drilling to create a gravity pipe, the only piece of pipe that's usable for gravity is really from E to D. The rest of the pipe is just put in there as a part of the process of getting to there. But I need to do from G to E and from D to B. Those two pieces need to happen. If they don't happen, I can't install the pipe from E to D. Therefore, I need a lead-in area and a lead-out area. That is one of the issues I need for directional drilling, because directional drilling starts from the surface, goes down, gets on line and grade, you drill along on line and grade, then you start coming back out again. Of course, if you think of the drill rod going through the soil, it is akin to a wire that's used for cutting cheese, right? As you pull that rod back and forth, the tendency is for E and D to start coming up and up through the ground, because the rod is under tension as it's being pulled either in or out. And so you end up having to move the E and D spots far enough away from the section that you want to use so that you don't end up pulling up. But that means that you do have a long lead-in area and a long lead-out area at the end of a used section of pipe. I'm using this from Ditch Witch. I'm using their directional drill and how they're going to explain how the directional drilling system works. So it'll go through exactly what I talked about a few seconds ago in the previous slides. So you're establishing the bore path. It's very important that you know exactly what utilities are in the way. And you generally will pothole those depending on the risk of those utilities. So they're drilling. You can see the drill rod is rotating, and you see that steel plate is on the front of it. Now they're going under the existing utilities there. You see that machine there that they showed us, the sound is sending up the signal. It's stopping at 12 o'clock. He's going to push straight, and then he pushed straight, and that caused him to go up again. So he's going along. Here they're talking about the mixing fluids. So that's the mixing fluid coming out at the front. That's the bentonite. It is mixing with the material, and it's going back and bringing the cuttings back. So they're using vacuum excavation here to expose utilities. Here it's getting to the end. So we've made the pilot hole in this case. Now what we're going to do is take off that drill piece on the end, and they're going to put a reamer on there. Here's your reamer going through, and it's increasing the size of the hole. Hopefully you'll increase it in steps and take it up to the final diameter that you need to do. Again, you're using bentonite in here to take the cuttings back. Pipe ramming, pipe jacking. Pipe ramming, pipe jacking is, as we demonstrated in a horizontal direction drilling, you need to lead in and lead out. Pipe ramming, pipe jacking, you start from a pit and you end in a pit. Or you may be pipe jacking, pipe ramming under a railway line or under a road which is built up on a flat plain area. Diameters up to 300, from 300 millimeters to 3.5 meters, 4 meters. You're generally not going to get 300 millimeters. So one of the problems that you get with pipe jacking, pipe ramming is that you may have to go into the pipe if there's something in the way, such as a rock or a tree, and obviously you can't get into a 300 millimeter pipe. The smallest you would get into would be either 450 maybe, but probably more 600 millimeter pipe. So therefore, pipe ramming, pipe jacking, you tend to put in at least a 600 millimeter pipe. When we talked about directional drilling a few seconds ago, we talked about making the hole 1.5 times or 150% of the diameter of the product pipe. That means you have an annulus of 50% of the diameter around the pipe. In all other methods of construction, you're only making a hole probably 25 to 30, 40 millimeters bigger than the outside diameter. That does tend to limit as to how far you can go, because your friction builds up depending on the soil, obviously, but 60, 80, 100, 120 meters, that's the limit. Whereas we talked about in directional drilling, you can go 4 or 5 kilometers if you need to go. Here's your pipe ramming. They have an air tool on the back, and they're hammering this casing through a road. You can see in this case they put a pit in here. Now by pipe ramming, I do not need a back wall because the energy I'm using to hammer the casing through, I'm essentially doing a horizontal pile driving. That casing is being hammered into the ground, and it has a little bit of extra pipe welded on the front leading edge to make an annulus a bit bigger than the outside diameter of this. I will also introduce bentonite around that casing pipe to try and lower my friction, and also to keep the existing ground in place, and create a little zone of low friction area to allow my casing pipe to advance as far as possible. And as I do ram in, of course, I'm building up weight on the inside because I'm encapsulating the material that was there in the ground originally inside the pipe. I will get to the point where my weight has come up because of that material. So I may stop, take off the hammers, take the whole thing apart, go in, clean out the material that's inside the casing pipe, reattach the hammers, and start going again. This is pipe jacking. Pipe jacking and micro tunneling are not that different. The only difference is the machine that's on the front end of this process. Pipe jacking would be an older process. You would have had people inside in that, up at the front end, tunneling by hand, just as they tunneled if you went way back to that brick sewer line that we talked about in Victoria, where they talked about they did the tunneling by hand. In this case, they used to do tunneling by this as well. Now we tend to use a TBM, or a micro tunneling machine, or a tunnel boring machine of some kind. So in this case, we're pushing the pipe from the back. Again, because we're pushing the pipe from the back, the annulus is only 25 to 50 millimeters on the outside of those pipes. You do tend to limit out after 60, 80, 100 meters. So micro tunneling and or pipe jacking are limited to those kinds of lengths before they start to slow down. Obviously, you can make the hole at the annulus a little bit bigger and continue on a bit more, and it depends on the soil types, it depends on lots of different things. Pipe ramming, pipe jacking, why you use one against the other. Back wall is one, and pipe jacking, I'm jacking against a product or against a wall. I'm using 250, 300, 400, 500 tons, that kind of numbers. So I need a back wall, a good back wall to push. In pipe ramming, I don't. My energy is coming from a pneumatic tool. So they both got benefits. And tunnel boring machine or a micro tunneling machine, very similar machines except to do with scale. So this is you can see in the front, in the middle of that, there's those three wheels in there. That's a trichome bit in there. That's the same type of bit actually that we use in directional drilling, except we just use that bit alone. We don't use all the rest of it. But this is set up to go through rock. Each of those gold-colored wheels, they rotate. They've got little knobs on them, which is very, very large material, which will eat away at the rock. Those wheels turn, and they chew away at the rock, and that rock cuttings then, again we use bentonite in this, so that area in front is all bathed in bentonite, shall we say, and the bentonite keeps those cutting edges cool. It also mixes with the cuttings, and it gets pulled back in and dragged back to the surface and separated out. We use the bentonite again, so very similar to the directional drilling system. We use the same in micro tunneling. And then if you look at the brakes in that machine, in the white colored pipe section of the machine, those brakes, they're actually hinges. And so there's jacks inside there that cause that hinge to move, which allows me to steer essentially. So I can steer vertically and horizontally, and I would have lined up this machine from the very back with lasers, and I can steer this machine. And I'm shipping in bentonite from the very back into the front, out into that cutting edge there, mixing with the cuttings that are coming off the rock as a result of those wheels that are chipping away at the rock all the time. And those cuttings are tending to flow to the bottom. They go in, you can see the holes on the bottom there. Those cuttings get absorbed in through there, or they flow in through there because it's pressurized, and those cuttings then are pulled back and back up to the starting process and put through cleaners and take the cuttings out. Here's a large tunnel boring machine. Now, we just talked on the micro tunneling machine. As we talked the pipe jacking, we're limited, as we said, to 80, 90, 100 meters because we're pushing the pipe from the back. Now we get into a tunnel boring machine, we do not push the pipe from the back. Once the pipe is put in place, it is not moved anymore. So what you're looking at is you're looking at the segments of pipe that are if you look at the right of that machine there, this machine is probably 2-3 stories high, in fact. So I'm trying to see it person, a human being in there, the scale of that, but it's probably about 5 or 6 human beings high. A channel tunnel, or it could be a tunnel through London for the tube, or through Vancouver for the SkyTrain. These are quite high machines, they're big, and so the pipe segments, they come in segments. They don't come in a whole circular pipe as you do in microtunneling. It comes in segments. The segments are on the top, and you can see the segments on the side there as they're put together. And so the segments are put in place, and then the machine actually pushes off those segments to go again. And it keeps on going that way. So the segments, once they're put in place, they don't move anymore. So therefore, the only friction in this is the friction between those segments and to the front end of the cutting machine. That's the only friction, which means the friction is very, very low, which means you can go, there is really no limit as to the distance you're going. We go back to the 1860s. So this is, when we talked about that slip lining of the brick sewer line in Victoria, this is how they would have installed it. Way back in 1860. This was Brunel's tunneling machine from the 1860s going under the Thames in London, putting in the tube in London. So again, you see that at the front face, they're digging at the front face, and they're putting the materials in, and then they're building the brick sewer line as they progress along, and you can see the jacks from that cutting edge, and they're pushing the front edge from the jacks, just as I did in the previous slide. They're pushing the micro tunneling or the tunneling machine along. In this case, they're pushing the face machine along by pushing against the existing brick pipe. Pipe bursting. Pipe bursting is kind of a hybrid between the two of them. So in pipe bursting, we are utilizing the existing pipe, but we're just using it as a hole in the ground. So it's a path that we're using to install a brand new pipe into. It can be either static or pneumatic. Static systems tend to be used in the north half of the US and into Canada. Pneumatics tend to be in the south half. Again, because the diameter of the pipe and the diameter of the hole that you make is only 10% bigger than the outside diameter of the pipe, you limit it to about 100, 150 meters. Not a big issue, because most of the time pipe bursting is used to replace pipe from manhole to manhole, and that would have been the length from manhole to manhole anyway. Diameters, it can go your water service for your house, which is 19 millimeters, all the way up to about 1200 millimeters. That's about the biggest you're going to get pipe bursting. Again, depends on the ground, depends on conditions, depends on the existing pipe and stuff like that. It is normal to upsize. So when we went back and we looked at the criteria for piping in the first place, we talked about the vessel to contain the liquid. Then the second parameter we talked was about the ability to handle the flows or the increase in flows because of densification and so on. This is how you increase the capacity of the pipe when the old pipe does not have sufficient capacity and we need to carry more liquid. Or if you've partially collapsed. If your pipe is partially collapsed and you want to replace the pipe and bring in a brand new circular pipe again, you can also. So what we're doing here is we're using it to replace a steel water main. Steel, because of its ductility, such as PVC, such as corrugated steel, such as ductile pipe, all of these products have ductility, and what tends to happen is that if you use a pneumatic system, you're hitting against the hammer just bounces back, so you don't get anywhere. So you have to use a static system that will pull, split, and pull again. And you're using, in this case, a steel water main. You're splitting apart the pipe with almost what looks like a can opener to put it apart, and then putting new pipe in. Because of the ductility of steel is not too bad. It will split and move out of the way. Ductile pipe has a lot more ductility and a lot more ability to spring back, because you're not taking the pipe up to its plastic limits. You're still within its elastic limits. You're still within its plastic limits, so it tends to spring back. So in ductile pipe, it is generally recommended that you do not go more than one size up, because it will tend to spring back and gouge the new pipe that you're putting in. Here is your typical replacement of a clay pipe in the city of New Westminster. The pipe, of course, has no ductility in it. It just breaks and moves into the surrounding ground, and you're pulling in the brand new high-density polyethylene pipe. Here was a job that was completed in the city of Maple Ridge a number of years ago. 2017-18. We burst a 375 pipe to a 950 pipe. That was a major upsize, 6 times increase in diameter. Detail on that one, but there's a lot of information on that slide actually. On the bottom right here, you've got that hole in the black pipe there. That's the bentonite going out to provide the lubrication between the hose pipe, the new hose pipe that we're putting in, and the surrounding ground. You can again see the difference in the head between the steel head and the pipe. You can see that 25-30 millimeter gap. That gap, so that steel pipe is making the hole, and then you've got that annulus now between the hole that you've made in the ground and the product pipe that you're bringing in. Again, it's the same type of event that you're going to have, whether it be micro-tunneling, whether it be pipe jacking, whether it be directional drilling. You're making a hole in the ground that's slightly bigger than the hose pipe you want to introduce. As we said, in directional drilling, you make it 50% bigger, but in all of the other processes, you're only making it 25 millimeters, 30 millimeters, 50 millimeters bigger. So you can see that hole is being made. That just decreases the friction to allow you to get that black pipe into place before the ground relaxes back around the black pipe and secures it in place. Then as I go along the bursting head and moving up along, I don't want to get into the soils issue too much, but in the very front end, up next to where the joint and the plastic pipes are, you'll see a little machine in there. That's it looks like pizza cutters. There's little cutting wheels in there that cut apart a plastic pipe and just pushed it out of the way, cut it, split it, and then moved it out of the way. Again, the reason there's straight sections in this was to do with the type of ground we were in. We were in very sandy soils, and so we were moving the ground out of the way. Once you push sandy material away or put compression on sandy material, you tend to cause the water to leave the sand. And of course, when you do that, then the material gets dry, your friction goes up. Then you want it to relax a little bit, so you get it to relax it and the water come back in again. Friction goes down, then you can start to move again. So that was the process that was being used there. Typical pipe bursting in a university, crossed through a playing field, did not want to dig that up. That was just a regular water main replacement. Here again, pipe bursting used to replace 450 millimeter concrete pipe up to an 800 millimeter pipe under a road. This was a job in North Vancouver. We were replacing corrugated steel pipe. Corrugated steel pipe had failed, and we were introducing high-density polyethylene pipe and corrugated steel. This was an area that the ground was actually polluted, so we did not want to dig in there, number one. Number two, the corrugated steel was full of material as well. Just doing house connections, replacing just house connections with using pipe bursting, very, very effective, much more cost-effective than open cutting. Here's typical of the pipe bursting, but what we're doing here is that because we're using trenchless technologies in general, we're either not digging at all or we're digging very limited excavations. In other words, if I was using directional drilling, I'd be similar to these excavations here. So all we're doing is we're reducing our excavation by 92%. So what we've done is, because we've done that, we haven't put a continuous trench right up through this alleyway. If we had done that, our alley the asphalt would have probably been degraded in 15-20 years. We'd have to replace it. Because we're doing this, we're not breaking down our asphalt, and it'll last 40, 50, 70 years. So we're reducing the amount of material that's coming out of here. We're reducing the degradation of the asphalt. We're not putting as much particulate in the air to replace the sewer line. So there's lots of benefits of using trenchless technologies. Cost comparisons, one of the concepts that comes out is that people say, oh, I don't want to use trenchless technologies, it's much more expensive and stuff like that. There's lots of studies out there that show that it's not more expensive. City of Langley, one of the cities that comprise the lower mainland of British Columbia, they often put out contracts putting both ways, asking for trenchless and open cut. They generally have seen about a 25% savings by using trenchless technologies in pipe bursting versus open cut. Other studies have shown, not just from British Columbia, but from the US, from New Zealand, that generally pipe bursting is about 25% cheaper. CIPP is about half the price of traditional open cut. Horizontal directional drilling is about 40% cheaper. Now, that won't happen in all cases, but we're just talking about general terms here. If in doubt, do that extra 3 or 4 pages, put it out in both ways. It's not a big deal to put it out both ways. This is where a lot of these information came from, and I'm using different products here and videos, and I thank the people I've used these videos from. Thank you.